Good morning, everyone. Thank you for being here for the presentation. I'm Avinaya Tripathi. I recently graduated from Arizona State University and I'm working there as an assistant research scientist. And I'll be talking to you about finite element modeling of 3D printed concrete, how there's orthotropic nature in the 3D printed elements, how we can decipher how failures initiate in the printed elements, how do we even build the material cards, the material parameters required to model these elements. So I'll start with like a general introduction of what 3D printed concrete is. Then I'll talk about why and how orthotropic natures and like anisotropic natures in printed elements come out. I'll then talk about how we can use one of the material card, MAT 213, that's built with like OSU, Arizona State University being there. It's implemented in LS-DYNA right now, so all my modelings will be based on LS-DYNA. And then I'll talk about some numerical examples, compression test and 4-point bending test, and I'll talk to you briefly about what could be the future use of all this work that I'm presenting to you today. So start with, again, 3D printing, free-form construction. You can construct different kinds of structures without having to actually create the formwork required for it. You could optimize your structures. You could even create like overhang structures to a certain extent. Again, with all those freedoms comes all different disadvantages too, in the sense of layering. You have like weaker interfaces and stuff. Basically, weakness of those interfaces kind of creates a problem usually in the mechanical responses and durability responses of the printed elements. In modeling terms, like there are a different number of challenges that we do have in 3D printed element, because in cast system we have like more isotropic kind of nature that we can model easily, while in 3D printed there is like how do you characterize the material that you have printed, how do you characterize it based on like the overall versus a single filament, how do you even check like the deformation that you initiate initially during the printing, how do you incorporate the interfaces, how do you even characterize those interfaces. So with all different challenges, again, there are different kind of solutions people have put in front of others, but again, this is one of the solutions we came through. So to start with, what is orthotropic nature? Like in conventional cast concrete, you'll most probably assume, even with fiber system, you'll assume like no directional dependency in the strength results, while in printed elements, without fibers also we will have directional dependency of strength. Let's say you do a compression along the print direction versus the build-up direction, you'll end up getting different results. And is it consistent over different mixes? No. Like as I will show you later, like some mixes might have a D2 direction very weak, while that might not be the case for some other mixes. So it's not like a given case that, okay, my build-up direction always will be the weakest. So those kind of things come into play. But again, as an assumption, do you assume or extrudate filament to be isotropic? Again, in our work, we have assumed that, because like, again, you are extruding a concrete, means like you most probably would have similar kind of properties in all three directions. And we are kind of calibrating the inter-filament, interlayer joints, the interfaces between the filaments. That's what giving you the orthotropic nature when there are no fibers. When there are fibers, that's again a different story. That I'll have like one or two slides that will show you how we can model when fibers are incorporated into the printed mixes. So in terms of the presentation, I'll talk about direction in terms of D1, D2, D3 a lot. So that's why I'm just gonna kind of clear out what those are. D1, basically I'm considering the print direction, wherever I'm compressing or putting a tensile load along the printed filament length, then that I'll call a D1 test. D2 is basically on the perpendicular surface on the same layer, basically on the width direction of the filament, and D3 will be top to bottom, basically on the build-up direction. I'll talk to you about modeling in terms of two of the mixes. One, as you can see, is I call it a L30 mix because it's a 30% limestone replacement of cement. And the difference between these two mixes being, this is also a 30% replacement with 10% limestone, 10% fly ash, and 10% slag. But the two major differences are, this is a 50-50 of cement and sand. This is a 60% cement, 40% sand. While water to binder ratio is different, like 0.35 and 0.18. We are doing the second mix to try to get higher strengths, like in the range of 100 ampere, while the above mix is around the 70 ampere mix. So what is required to model all this? First will always be the experimental data, like to generate even validation numbers, what do you validate it against? So you will need validation numbers as well as the parameters to input in the material card. So it will all start with generating the actual experimental data based on cast samples and printed samples. And then we'll talk about how a predictive FE model could be built based on all these parameters and based on like two of the cards I'll be using, one being the MAT 213 that I talked to you about, and another being a MAT 186, a cohesive zone element model for the interfaces. Then I'll kind of in between talk about how the calibration process were done, how we are ending up with the results we are ending up with, and how this will be like a constitutive model for like predicting the failures and predicting strengths based on different mechanical tests. So to start with, again, required test, we are doing two different types of tests. One is compression and one is 4-point bending flexure. We basically do not test as printed. We print a big slab from which we usually take out uniform beam sections and cube sections. Again, if you do not take uniform beam sections and cube sections, there will be other different things you will have to consider. The filaments not being straight enough might not give you a very flat surface to load and all those things. So to stay away from those problems, we always cut it out into regular shapes of like the cubes are 60 by 60 by 60 millimeters, and the beam is a 60 by 60 by 300 mm beam. And the 4-point bend test is done on a 240 mm span with 80 mm being the loaded middle third. So in flexure, again, I have not done D2 and D3 because it might in turns be like characterizing the interfaces, but it's not actually the case as we have seen in some of our tests that we did, because the numbers are all over the place in the sense of like, do we assume a certain kind of strength for the filaments, then the crack do not technically go through the interfilaments always, and resulting on a more kind of a heterogeneous kind of strength results that is not actually of the interfilament nor neither of the ball filament. So I'm staying away from D2 and D3 for the beam test. I'm just doing D1 for the beam, while for compression we are doing D1, D2 and D3 as I described before what those are. So based on two of the mixes, as I told before, the L30 is a 70 MPa kind of mix, while the UB is a 100 MPa kind of mix. And as we see, like the thing I mentioned before, if you see L30, you see that the D3 direction, that the build-up direction is very weaker in comparison to the print and the width direction, while in UV you do not see those things. There are different reasons for this. The first thing being L30 mix, it's a slightly stiffer kind of mix with low SP percentage. So when you print it, because we are printing a slab, you are printing the filaments side by side without little to no pressure exerted in between, and the filaments become weaker. While the 10 mm height, sorry, I should have mentioned this before, the filaments are 10 mm height with 20 mm width, with a 20 mm nozzle. So when you are printing a 10 mm, you are kind of putting a pressure on the top of the filament, kind of consolidated. It's not going to be similar to doing a cast sample, but you are kind of putting that pressure to avoid voids and stuff. So in terms of that, the interfilament becomes weaker. But why would you not see the same thing on a UV sample? Because in UV, it's a low water cement ratio mix. So to make it printable, we had to add more SP. So as the auger that we have extrudes it rotates the mix, and if you have seen a UHPC mix, a thick kind of UHPC mix, you will see that once it's stirred, it looks like water, while it's setting, then it looks like solid. So technically, let's say you are printing filaments side by side. Now this UHPC comes as more of a liquid out of the nozzle, and as soon as it sets, it makes a good connection with the filaments, but the next layer that comes above it will always have a delay, and kind of like, it's like you are trying to put a fluid over a solid kind of surface. So the interlayer and interfilament strengths are slightly different in terms of UV in comparison to the L30 mix for the higher cement ratio. Again, this could have different other applications in the sense of like, oh, do you want to do a lower water cement ratio, higher SP mix so that you don't actually get much of orthotropic nature or anisotropic nature? That could be another thing of study. But in terms of flexure also, typical things that we see, the cast sample performing better than the printed samples. I'll use this for validation, so just I'm showing the results here for the moment. But in terms of numerical modeling, the biggest challenge comes here. How do you model this? So what we assumed are, I'll talk about the assumptions later on also, but we are taking each individual filaments as an isotropic, at least for now. I'll show you why when it's not isotropic. later on in the slide, but we are assuming because there's no fiber or anything, it's like a filament, isotropic filament being extruded. So your D1, D2, D3 direction parameters are same in the filament. But now how do you incorporate the D1, D2 direction compression being different? That comes into the interface, like the inter-filament, interlayer joints, where you are giving the strength to interlayer, inter-filament joints, and we have seen in different tests that actually in printed elements, the compression test, even if you do a cube, is not actually a shear failure kind of test where it basically has a vertical kind of cracking through the interfaces rather than the overall shear failure of the cubes. So that's our concept of it, like it should be initiated by the interfaces rather than the whole filaments. So again, as I told before, two different cards being used for filament MAT 213 and for interfaces 186. I'm not going to go into too much detail about 186 because it's a cohesive zone model that basically has a tensile parameter and a shear parameter to it, and tensile failure energy and shear failure energy. But I'll talk to you about MAT 213 because that's a model that we developed in ASU itself. Professor Rajan has worked a lot in this material, and they are trying to incorporate it into concrete. What's the advantage of this material model? Like, I'll talk to you about the advantages, which I'm not using as of now for this, but I'll show you how it's used in later slides. But the biggest advantage is like it allows you to actually separate D1, D2, D3 parameters. It allows you to provide different coupled damage, uncoupled damage in these directions, and provide different stress strain curves based on. They develop this for composite layers basically, because they have fibers in D1 direction. They will have different parameters in the 1 direction, 2 direction, 3 direction. So they develop such that you can decouple every directional parameters, the every directional stress strain response. So which could come into use in printed elements. So we are using MAT 213 for that reason. There are like different kind of failure parameters that they have defined. They use like, we can use different, but we are sticking with the tabulated failure criterion for our use. But again, we can extend it into having different more checks for the failure. Now, when I say you can provide different stress strain curve in different direction, this is a typical stress strain curve in one direction. So you could, for now, because I have the filament as isotropic, I'm going to put the same curve for direction 1, direction 2, and direction 3, but you could choose to do different directional parameters for the material guard. You can, let's say this one is about 70 ampere, then I can go another direction at 50 ampere. Again, that will be a user-specific case scenario, but for our case scenario, we are using, at least for the initial, these two models as the same parameter for D1, D2, 3 direction. So you see like there's a vast number of parameters in 213 that you have to actually input, which is simplified by the isotropic assumption, because you will see like 3 direction has the same E parameters, same Poisson's ratio, same sigma 2, all these, like because we have assumed isotropic, it kind of cuts down everything by 3. And there are like few parameters like the shear modulus we are estimating based on isotropic E, G, nu kind of relationship. And another thing that we are estimating is the shear stress, which I'll talk to you on the next slide also, I guess. But as I told before, the filament is assumed isotropic, cutting down the parameters by 3. Shear stress is assumed to be the function of tensile stress, where we are using, I think, 1.45 times the tensile strength for the shear strength. That's one of the estimated parameters. And there are 2 parameters that we are calibrating right now. Those are the equivalent failure strength, the GTFC failure criterions that I was talking to you about, because we want to initiate failure at a certain point of time, and we do not exactly know these strength parameters. We are calibrating it for this. So with this material card, the only parameters we are calibrating will be the where you actually want to see the failure at the material level. And with MAT 186, because again, we do not have a lot of data, or I'll say not significant data in terms of interfaces that we can actually have all the numbers for this. So this is highly calibrated in the sense of where the failure actually initiates. In this calibration process, we have used some literature values where we get like the first initiation peak for the fracture from literature, where they have used a ratio of 0.02 for mode 1 kind of fracture and 0.25 for mode 2 kind of fracture, and others are calibrated. So based on all these models, like again, these are cube models. We use the quarter-symmetric model for this, similarly quarter-symmetric model for the beams, and based on this, we calibrate parameters, as I told you before. There's a single another calibration that goes into this work, that is the failure on the tensile side. So to make it easier, we have come up with a solution in the sense of flexure, where you use the actual failure parameters from the compression, divide it with the compressive strength, and then multiply it with the tensile strength of the material. And that's your failure parameter for your direction flexure. And these are like the calibrated, after the calibration and all the program done, these are the first graphs represents your experimental value. Second is the estimated parameters. They are kind of showing the anisotropic nature as well as capturing the actual strength. This is for a different layer heights. I think I have like less time, so I'm just going to go quickly on through it. So these are for different layer heights. And this is the major thing we are observing, like when does the failure initiate. Like if we see the failure initiation starts with the cohesive zone parameters, like the cohesive materials deteriorating, and at peak, though not seen in most of the cases, the MAT213 actually starts to deteriorate at that point of time, showing that that's kind of showing what we see in the experiment, where the interfaces are eroding first. And these are the experimental versus the AFI model stress strain curve for a representative sample that I'm showing here. It's kind of closely replicating what we see in experiments. The biggest use of this MAT213 card comes when there is fibers in printed element, because in printed elements you will have like fiber oriented along the print direction. Now your D1 direction property becomes drastically different than D2 and D3 direction. So how does it use? So based on the UV, we had the UV without fiber calibrated before. So if we have a UV with fiber, then we see this kind of flexural response. Can we replicate this flexural response? That was our goal of the work. And basically keeping everything that I showed you constant, we only change the D1 direction tensile parameter. And based on this, like with calibration, we see that we can actually replicate the flexural response of the still fiber sample also. For the future scope of the work, again, like the orthopedic material models, basically for fiber sample is the biggest use of modeling through MAT213. We are trying to do like multiple economical kind of material composite sections that we want to model and see optimize these sections also. And the biggest challenge will be always characterizing the interface so that we actually get the experimental value in these models. And modeling some fresh state modeling also is required. So with that, I'd like to thank the funding agencies, NSF, US Department of Energy, and my professor, Professor Narayan Neithalat, and my senior, Suraj Nair. Thank you.
Thank you.